will discuss about the future of electronics, specifically related to the 2D materials for spintronic devices. Actually, if we talk about the spin electronics, it's kind of a specific or special type of branch of physics or electronics which deals with not only with the charge current but also with the spin current. Similarly, we talk about the quantum electronics, that is normally affected with the quantum effect devices. Since quantum effect devices means you are studying the quantum phenomena in those devices. But in some cases we can see some devices will have both spin electronics as well as the quantum electronics effect. First question is, why we need these spintronic devices in our industry? Normally in most of the cases you can see people are working on the low power devices. In the case of low power devices, you need a more degree of freedom to operate your device. In normal cases, we only see the devices operate due to the charge current. Like you have a transistor, you have a diode, you have other power electronic devices. But if we increase the degree of freedom, means we add one other parameter, then what we can do, you can have the more opportunity to design a new structures, a new devices, new storage devices, in some cases data transfer devices or low power devices. My group is working in the different fields in which one of them is spintronics, others are heterostructures, energy devices, quantum electronics, and sensors and field effect transistors. These are just a few of them I have mentioned here, but I am working also in some different fields. Today I am talking about the spintronics only. Normally we are working nowadays on the energy devices. This is kind of a diverse field. On the spin electronics, you cannot find most of the group you can see are working on those materials that is commonly available. But if you see the spintronics or spin electronics, you cannot find a single group in Pakistan that is working on this field. The reason behind that, the field is unique, field is tough, getting outcome is difficult, generating new ideas is difficult. So no one actually get into these kind of fields. But if you see the good groups in all over the world, they are focusing on those fields which are unique in nature and you can get a result, you can make the breakthroughs. That's why you see in the Harvard, in MIT, in Georgia Tech, in Germany, in some groups, Stuttgart, they are working on these fields. We should know, we cannot get the output very quickly. As I work in this field, I got first of my result after 1.5 years. It is a continuous effort, and after that you get succeed. I am talking about the 2D materials. Is one of the famous field, 2D materials. In the 2D materials, the Nobel Prize was given to two scientists in Manchester in 2010. It was theoretically unpredicted that we cannot make any kind of two-dimensional materials. Because when we decrease the thickness of any layer, it becomes unstable due to the thermal effects. If it will be unstable, means theoretically it is possible, experimentally it is impossible. But the first time in 2004, one of the scientists his name is Andre Geim, and his student, postdoc fellow, Neboslo, they first time they observed the layer of graphene. The layer of graphene is kind of sheet of the graphite that just peeled off from the bulk graphite, and they study the electrical properties, they study the optical properties, they study their mechanical properties, and after 6 years they got the Nobel Prize. There's a discovery of new material that is not naturally exist in the world. No, people try to find other materials like HBN is the boron nitride, MOS2 is the dichalcogenides, molybdenum disulfides, and WSC2, and so on and so forth. Because this invention of these materials or discovery of these materials gave the new direction to the further research. Now the next step is how we can use these materials for industrial applications. One of these applications is a spintronic device. How the spintronic devices work? In normal case, if we discuss about the transistors are a simple device. If you talk about the field effect transistors, in the field effect transistor, what you do, you apply the current or you apply the voltage and you measure the current. In that case, if you see this kind of behavior, you have one electrode and you have a channel, you have another electrode. You apply the voltage, you measure the current. Alright? By applying the gate voltage, you can tune the conductivity, tune the mobility of the charge carrier through the channel. But in the case of spintronic devices, in that case, you are actually measuring the charge current. You are flowing the charge through the channel and measuring the drain current. And normally, the electronic devices in the electronics we normally study. The electrode we make is normally metallic in nature. It might be a gold, it might be a silver, it might be copper. In that case, charge carriers, the moving charge carriers normally exist in the form of random orientation. The random orientation means your charges are flowing, but the net magnetic moment of that charge carriers cancel each other. And we have only a charge current flows through that channel. But in some of the materials like the ferromagnetic materials, if you apply the magnetic field, those charge carriers can be aligned in one direction. If these are aligned in one direction, then we have increased 1 degree of freedom. Means we have the charge current as well as we will have the spin current. If we will have both charge and spin current, then we can make the spin electronics. We can make spintronic devices. We can make spin FETs. We can make spin transistors. We can make spin wall devices. These kind of devices can be utilized for data transfer, can be utilized for data storage. Actually, the same kind of behavior is normally used in the hard drive. So I will talk about the spin wall devices today. In normal transistor, you have the channel, you have the 2 electrodes or 3 electrode or 4 electrode assembly. You apply the voltage, you measure the current, or you apply the current, you measure the voltage in normal case. But if you have the ferromagnetic electrodes that I have previously shown, those kind of electrodes that are polarized. The polarized means you have the charge carriers, moving charge carriers, but they are aligned in their magnetic moments. If they are aligned, then what you can do, you can see in that case, in the bottom side, you have the electron in aligned spin, in aligned magnetic moment. What will happen? They will inject this polarized electron to the channel. Although the channel, if the yellow strip is representing the channel, means electrons are injecting with the polarized spin. When they are injecting in the polarized spins, you are applying the current on the one side, you are measuring the voltage on the other side. In normal case, when you do the measurement, your current means voltage should be measured within the channel. Within the channel means if you are applying the source and drain, your inside voltage should be measured. If in the case of 4-probe measurement, If you have a transistor, if I talk about the FET, what we do, we apply the current here and we measure the voltage. Means what you are doing, you are measuring the voltage within the channel. That is known as local measurement. The current is flowing and we are measuring the potential difference between the two terminals. In normal case, because charges will flow from this point to this point and there will be some potential at that channel, that electrode, some potential will be at that electrode, we can measure the delta V, actually the potential difference, and that potential difference we can calculate. I is equal to, you can calculate R is equal to V, delta V over I, the resistance of the channel, or you can calculate the conductance of the channel. But in that case, if you are applying the voltage, you are applying the current here and you are measuring the voltage on that point. A current path, if you see the current path is this one, charge current is flowing in that region, and you want to see the effect on the other channel where there is no current is flowing. If there is no current is flowing, in general, in normal case, in classical case, you cannot see the current because the current path is not following that region where you are measuring, you want to measure. If you see some kind of effect in that region, what will happen? You will see the diffusion of electron, of the polarized electron, that can create the potential difference between these two electrons. And this change in the potential difference on these 2 points, it should be the spin current, because the path of the charge current are these two electrodes. It should flow between these two electrodes, and you are measuring the current on the other region, that is due to the diffusion of the electron or spin polarization of the electron at the other end of the electrode. Right? If time is short, I can discuss in detail if you want later. This method is known as lateral spin transport. Charge is flowing, and if the charges are polarized or spin is aligned, you have the charge current as well as you will have the spin current. In that case, you can see the path of the current is different from the measuring voltage. The measuring voltage region is different. It means what is happening, you are measuring the only spin current. If you will measure within the region, then you are measuring the spin current as well as the charge current. In other case, you can also vertically transport the spin. You have a top ferromagnetic electrode, you have a bottom ferromagnetic electrode, and you have intervening layer, or also called interlayer. Actually, the word spin valve actually comes from the interface, the barrier between two ferromagnetic layers, barrier between the two spin junctions. On the first side, you can see if you have a two electrode, I can show you here. Simple phenomenon. In the hard drive, what we do, you have a ferromagnetic electrode. On the bottom side, you have a top electrode that should also be ferromagnetic, and you will have an interlayer. Interlayer means the electrode, the layer that should not have ferromagnetic in nature. Those material may be conducting, or gold can be utilized. Gold is a conducting material but non-ferromagnetic. You can use copper, you can use aluminium, you can use gold. All these materials are known as the non-magnetic material, or known as normal metal, which should not have a ferromagnetic in nature. What will happen when you flow the current? Only charge current passes through that region, through that junction. I can make here, you have a ferromagnetic. Suppose these electrodes are aligned, polarized. Bottom electrode is also polarized. in the same direction or in opposite direction, and there is a region that is unpolarized electron. It means you can only transmit, only transmit the charge current through that region, because when the spins will go into that region, it will be filtered out. So you can change this, you can calculate the spin current at that region, you can see the spin alignment or polarization at that region. When you will have actually this spin polarization tells you the bits 0 and 1. If both spins will be in the one direction, you will have the low resistance of the junction. Low resistance means you have a raising of the data. If the data only will be received or stored when you will have the high resistance. I will tell you here, you have a junction. In that case, we are talking about 2D materials. The intervailing layer is graphene here. You can see red electrode is the one ferromagnetic electrode. Top electrode is another type of electrode with ferromagnetic in nature. You are applying the current with magnetic field, you are measuring the cross junction voltage. At that junction, actually current is flowing through the barrier. That barrier is a non-magnetic. Means just charge current will flow. We are filtering the spin of the top electrode and bottom electrode. When we apply the magnetic field, what will happen? These charge carriers will be aligned, polarized on the bottom side and will be aligned on the top side. And when the switching of these charge carriers will be opposite to each other, means the orientation of the spin will be opposite to each other, you will have the junction resistance at the higher level. When resistance will be higher, you will have the higher resistance state. When both charge carriers or spins are aligned in one direction, you will have the low resistance state of the junction. Then what you are doing, you are creating the two kind of states, that is high resistance states and low resistance state. That is actually 1 and 0 bit memory. If the both spins of the both electrode, bottom and top electrode, are aligned in one direction, you will have the low resistance state. If you have one direction is opposite to the other, in that case you have a high resistance state. If your data is in the 0 bit here, the data at that point will be a 1 bit here. And this case is known as a spin valve device. Means you are adding, you are changing the magnetic field, you are storing the data. In some cases, like in the RAM, if that will be too quick, you can only store a data for a few milliseconds or a few microseconds. Means you are storing the data and transferring the data. That is known as temporarily data storage device. What you can do, the change, how much if you will have a large change in resistance, that is known as the magnetoresistance, normally known as MR. That is the resistance, higher resistance, that is your low resistance. The higher resistance minus low resistance over the R naught is your change in resistance, known as magnetoresistance. If we change this interlayer with the insulating layer, means this intervening layer may be conductive, may be non-conductive, may be metallic, may be insulating. If this layer will be a metallic layer like copper, metal, gold, these devices are known as spin valve devices. If this layer is replaced with some insulating layer like aluminum oxide, HBN, silicon oxide layer, thin silicon, then you will have a tunneling effect. These materials, spin valve devices, then converted into the MTJ, magnetic tunnel junction. So you can see the tunneling effect, as well as in that case, if you are using an insulating layer between these electrodes. The story is very simple. You can make the MTJ, magnetic tunnel device. You can make a spin valve device in the both cases, interface is very important or very critical. If you have a clean interface, you can get the more clear signal. If you will have a large change in the resistance, you will store more data. If the range of this plateau is greater, then you can retain data for a longer time. Now the question is how we can improve the magnetoresistance, how we can improve the retentivity of that region is totally depending upon the interface. The interface between the intervening layer and the ferromagnetic electrodes. If we change the layers, we change the thickness, the properties will drastically change. So this one is the motivation. We can try different spin wall intervening layer. Here I tried with the graphene layers, WS2, HBN, graphene HBN, and graphene aluminum oxide. These are some setup that has been used for these experiments. Lithography, we use the lithography. Photolithography, we use the e-beam lithography, then some deposition techniques, and then for the characterization, Raman spectroscopy was used for the initial characterization, and for low means magnetic characterization, we have used low temperature measurement setup as well. This I am going to pass this one. If you have question, you can actually. This is the method how you can make the device. If you are interested, I can talk about that. All these are the lithography setups, and here I will talk about this little bit about the structure of the spin valve device. The question is why the spin polarization of the top electrode is different from the bottom electrode, or how we can make such devices in which we will have a different polarization. First point is you should have, if you have a different electrode, different ferromagnetic materials. Suppose on one side I am using nickel electrode, on the other side I can use some other ferromagnetic electrode. The corrosivity of those materials are different. I mean, if one material is aligned at 0.15 Tesla, other one may be 0.55 Tesla, could be aligned. Means you are creating the difference. You are applying the same field, but the point of switching point for top and bottom electrode is different. Even you can also make this part in the same material by changing the thickness of the device, by changing the width of the electrodes. You can create the difference. That is very important to make these regions. Only possible when you have, if both have the spin orientation at the same magnetic field, then you will have the sharp increase and sharp decrease in the, then switching point will be very critical. So this one is a real device. The wide strip is bottom electrode and thin strip is top electrode, and you can apply the magnetic field at an oblique angle. You can apply the current and measure the voltage. This is the first case we studied. We apply the voltage and also apply the magnetic field and see the effect. This same kind of behavior we observe in the single layer graphene. This one is the first experiment in the Spintronic devices that has been performed anywhere. There was some experimental prediction that we can do this kind of theoretical prediction that we could do this kind of experiment. First time we studied the graphene or 2D material for Spintronic device. All those signals, if you see the magnetoresistance is very low, is 0.09%. That's too low. Then we tried to improve by increasing. We thought that the intervening layer is very thin. We were using graphene having thicknesses 0.3 nanometer. So what we did, we increased the thickness. We used a bilayer or double layer. What happened? We're increasing the thickness. You can see it increased to up to 0.27%. At this stage, the value is not important because we were not more concerned about the values. We were concerned about the idea whether our idea is acceptable or not. In the same time, when I was doing this experiment, the same group, one group from the Naval Research Lab, USA, they study the same junction. We were in the parallel. And what happened? They published one of the article with opposite results, that the graphene works as a tunneling layer instead of a conducting layer. But my results were totally different when I see the IV curve. If I have shown here, okay. We saw that in the case of graphene, it was a linear result, like a linear IV. And it was very difficult if you have a good results from a very big group, and you have to contradict the results. What happens? We tried with the different samples, and in all cases the result was similar, that the junction shows a linear behavior. That was the turning point. We actually contradict the results that already published, and we publish our article on that the junction graphene spin valve works as a conducting barrier junction. Although it was difficult in the start, then we tried to do the different materials, and we studied with the WS2, with MOS2 intervening layer, with HBN intervening layer. And later, after 4 or 5 years, the same Nobel laureate group started work on the Spintronic devices. Then they studied our paper, and also they studied their paper that was published in the same years in 2012. Then after looking at our results, they have written one paragraph that after multiple experiments, we have concluded that this junction is a conductive nature. Then that was a very plus point if one of the Nobel laureates are appreciating your results, and they published the paper in the Nature, and I was the reviewer of that paper at that time. And what happens when I see that they said we have tried many samples, I think it's 36 samples or 25 samples, and we have seen this junction is conductive in nature. So this was the one initiative that we started with the blank idea. We don't know what is the result. We don't know what will be the outcome. We don't have any literature, and we published. We worked, and in the later one of the group from you may know Albert Ferret group in France. They got the Nobel Prize in 2007. The same kind of work they also published with our citation. So if you think, the values are not important at that point. The idea is important. We floated the idea. The improvement is the next step. You generated the new idea that was not published previously. Some other one will do the work. They can increase the performance. They can improve the performance of the devices. But step is scientific. For the scientific knowledge, you have introduced a new field of spintronics, graphene spintronics in the market. After that, I wrote many papers on the spin valve devices. In the case of memory devices, you can see if you will have, look at this region on the right side. Actually, what memory is? You are increasing the voltage. You are applying the voltage. You are applying the current. You are measuring the voltage. And with the sweep of magnetic field, you are increasing the magnetic field. When you are increasing the magnetic field, what will happen? At one magnetic field, you can see two resistance peaks. In the one sweep, if you are decreasing the magnetic field or you are decreasing the magnetic field, in both cases you have two different resistance peaks. Means at the one sweep you are increasing the resistance, in the reverse sweep you are decreasing the resistance. If you see at the zero magnetic field, you have a blue line and red line, and the blue line has a low resistance, red line. In the same magnetic field, you have, one case is the storing data, and one case is erasing data. If you see the red line, that is erasing the data, decreasing the data. Means your stored data will be decreased. At one end. On the other end, you are storing the resistance, or you are storing the data. So this one was the idea how you can make a new direction or new field. There are many questions arised: the thickness, the quality of the junction, how you can improve the quality. In some cases, you can, in the first slide, you can see the first graph, the noise level is too high. Means we were not able to control the barrier interface performance. If you will have a rough performance of the device, what will happen? You will have the noisy signal. Actually, you are not clearly filtering the polarization of top and bottom electrode, right? And if in some cases you can see, we can observe a very clean signal. Means noise level is decreased. It means you can make good devices by creating a good interface. And I have published many papers, around 14 papers on this article, you can make a good device with improved performance. I can also talk about a little bit about the polarization of, but I think time is short, so I can just conclude. And later on, they invited me to write a book in contribution with the different journals, with authors, some of them from the Cambridge, some from the University of York, and the same work I have published in that book, that is on the Spintronic 2D material. For the research student, that's very important. Mostly students follow the values. They were concerned about how good results you have. In some cases, your results are not very important. Values are not important. Your idea is important. How you can say that all the time we will get the good results? It's not possible. If you are a researcher, you should know. In all cases, you will not get the good results. In some cases, you will get the better results. In some cases, you will have maybe lower value of your results. But the idea is you should not be concerned about your values. Means if you will increase 10 times values, you have done nothing. Actually, if you have created the new idea that is not published previously, a unique idea you are publishing, that is your contribution to the community. So focus should be, what is the new addition in the scientific community? New addition is not the new values, new numbered values, or performance enhancement. This is one factor. If you are creating the new idea that is not previously published, previously introduced, that is your contribution. I think graduate students should contribute in such a way. In MS or PhD, you should have one unique idea that is not previously published, or what is your contribution in your group as master's or PhD student. Thank you.